Bienvenue à tous. Je m'appelle Peter Jackson de la Université du Nord de la Colombie-Britannique. Je présidais la séance plénière d'aujourd'hui. Merci à tous d'être venus. Welcome, everyone. Just a sec, I have a problem with my video or my audio. Welcome, everyone. I'm Peter Jackson from the University of Northern British Columbia. I'm chair of today's plenary session. Thank you all for attending. I would like to start by acknowledging the Indigenous peoples of all the lands that we are on today. From coast to coast to coast, we acknowledge the ancestral and unceded territory of all the Inuit, Métis, and First Nations people that call this land home. La présentation de ce matin s'intitule Le golfe du Saint-Laurent soumis au réchauffement et aux événements extrêmes. Il sera présenté par le Dr. Peter Galbraith de Pêche et Ocean, Canada. This morning's presentation is titled The Gulf of St. Lawrence Undergoing Warming Conditions and Extreme Events. It'll be delivered by Dr. Peter Galbraith of Fisheries and Oceans, Canada. Dr. Galbraith is a DFO research scientist in physical oceanography, whose main interest is the climate of the Gulf of St. Lawrence. He's chair of the Atlantic Zone Monitoring Program and is responsible for delivering State of the Ocean advice. He produces the annual State of the Ocean report for the physical oceanography of the Gulf of St. Lawrence and leads the production of the Zonal Environmental Overview. He contributes to DFO's monitoring program by running a helicopter-based winter survey of the temperature and salinity conditions in the Gulf of St. Lawrence. This morning's talk will be roughly 45 to 50 minutes long, to leave about 10 to 15 minutes for questions. I ask that you type your questions into the Q&A box. If you indicate your name in the question, that would be most appreciated. And I will read the questions out and Dr. Galbraith can respond to them at that time. So with that, I am just going to stop sharing my screen and ask you, Peter, to share your screen and we can get started.
Great. There we go. Guess I'm going to move this little screen here where can't see you. Minimize it. Okay, there we go. Well, first, thanks for the invitation. It's very nice to give this plenary talk. This is sort of a modified presentation that I sort of give annually on the state of the ocean. So I have lots of various material to show, and I'll be switching subjects quite a bit over the course of the presentations, as we'll see. So the presentation is basically about the physical oceanography of the Gulf of St. Lawrence, which is pictured here, which is traversed by a deep channel that goes out to the continental shelf called the Laurentian Channel. It's 300 to 500 meters deep and shallows fairly quickly within about 15 kilometers to only 15 meters depth at the sill in front of the Saguenay Fjord. It's about 250,000 square kilometers, and it's characterized by, in summer, by 3 layers that I'll be talking about. And I'll be talking about the origins of these layers and how they relate, how they're created, and their interannual variability in terms of forcing, mostly air temperatures. And this gives us an aspect of the past variability is the key to explaining the future. If we can link how the surface temperature or collimator temperature is linked to air temperature, then it helps us even a climate change tool. So the 3 layers are shown here with sort of a temperature profile. So depth on the Y scale and temperature on the x-axis, sort of a flipped oceanographer's view of a graph. And the 4 lines show the various seasons, basically, in the Gulf of St. Lawrence. And the surface layer, pictured in red here, is typically in equilibrium with atmospheric air temperature. And beneath that is a cold intermediate layer that's formed the previous winter. And below that, we have a deep layer that feels no seasons, that has no exchanges with the atmosphere. So there are changes there, but there are interannual, much slower, and caused by estuarine circulation. All of the data, most of the data that I'll be presenting are from the Atlantic Zone Monitoring Program, which is a DFO program run across all the regions of the Atlantic, whereby we use the same methods on ships to obtain physical and biological oceanography sampling up to zooplankton using the same methods and using the same reporting structure so that we can present a unified report annually of the state of the ocean for the entire zone. For the Gulf St. Lawrence, we actually cover the Gulf 4 times a year. So 2 of these surveys, these are showing the station coverage for 2023. So we have a June survey and a fall survey, and you can recognize the lines, the AZMP lines that were on the previous maps. And we also instrument do oceanography on the August and September groundfish surveys, where basically DFO fishes for various species to do stock assessments, and we will do oceanography using a rosette and also using a CTD attached to the trawl itself. And in the winter, I run a helicopter survey where I sample the Gulf St. Lawrence at about 100 stations while the helicopter is in stationary flight at about 100 feet in altitude. So do this every year. So we have coverage, the full water column, about 4 times a year, so we can pick up not only interannual changes, but seasonal as well. So since air temperature is the main driver, that's what I'm going to show you first. So the data are from Environment Canada, and it's their homogenized data set that's used for climate change research. And there are 13 stations here pictured around the Gulf St. Lawrence, which I've averaged together and show here on the top panel the annual thick line and monthly, the gray line, anomalies. And sort of you can see over the last 150 years or so, the warming trend of 1.6 degrees C per 100 years. And I divide up the year between a winter part, December through March, and a April to November part, so ice-free sort of portion of the year. And you can see here that the overall, the winters have been warming almost twice as fast as the summers, at 2.3 degrees per 100 years, whereas we're at 1.2 degrees per 100 years in the April to November period. Although there is a hint that the last 40 years or so have been faster than the overall trend, faster warming. Looking at SST, this is a 26-year climatology of what the SST looks like in August, sort of, because then I'll be using averages, but I still wanted to give you an idea of what it looks like spatially. You can kind of tell there's a north-south gradient where the water's above 20 C or around PEI and the Madeline Islands. But the gradient isn't as pronounced as you might think it might be when you reach latitudes of up to nearly 52 north. The water is still quite warm in the Northeast Gulf, and the cold spot is actually the St. Lawrence Estuary. And you can see this coal tongue here that looks like it's water flowing out of the Saguenay Fjord. And actually, it's the cold intermediate layer that is beneath the surface layer that is getting mixed at the head of the Laurentian Channel. I mentioned earlier that the Laurentian Channel ends abruptly here, shallowing from 350 to 15 meters only. So imagine basically a stratified water column, and you've got a tide sloshing water back and forth in the estuary on this slope here, and that's creating a very strong, high amplitude internal tide, which will have a wavelength of maybe 40 to 60 kilometers in length, but an amplitude that can reach up to 50 meters at the generation point. So there's lots of shear associated with this internal tide and lots of upwelling of the water close to the surface, so lots of mixing. So this cold tongue is actually cold intermediate water that comes, I say poetically, that it comes to die. The winter waters come to die in the St. Lawrence estuary every year, every summer. And you can note a mixing spot here in the Îles Mégane. So again, a tidal feature that is mixing up waters here. If we do over all of these 13 Met stations, a 30-year climatology of monthly air temperature, we get this gray line. And if we do AVHRR, the same climatology that I just showed you, but weekly, basically, over the same 30 years, then we get this dark line. And you can see that they're very similar, but before the temperature maximum in late July, the air is warmer than the water, so the air is warming the ocean. And after the maximum, it's the reverse. It's the air is cooling the ocean. And if you actually move the climatology, shift it by 2 weeks for air temperature, they almost perfectly overlap. And I didn't even fudge any numbers here. They're just the straight climatologies of the two things. So this is sort of like the first climate change tool, is that this is a 30-year climatology of the season. But if it shifts in 100 years, then we can expect that the SST will follow whatever the air temperature is doing. But it's actually stronger than a 30-year climatology in terms of linking SST to air temperature. If you look at the May to November average here of SST, it'd be corresponding to the area under this curve. And same for air temperature if we extend it to April to account for the shift, the 2-week shift. So basically, if a year it's warmer, we get more area, more average temperature from May to November. So it's really the area under this curve. So here I'm plotting the SST over the Gulf of St. Lawrence, one number per year, May to November average. And you can see this from satellite data from 1982 to present, well, last year. And I do the same thing with my air temperature stations. And you can see that I'm picking up 72% of the variance with air temperature and SST just in interannual variability of the area under this curve. So I can use air temperature as a fairly good proxy of what the SST was for 150 years or so. And this gives us a warming trend, very similar, of course, to air temperature itself of 1.1 degree per 100 years, with fairly high confidence. And you'll notice that the last 3 years have been like over 1 degree C. We're talking about 1 degree C per 100 years, but the last 3 years have been over 1 degree C over this trend line. So very strong anomalies for the last 3 years. We don't expect this to hold. It's going to drop down close to the climatology at some point. But it's really surprising to have seen this very strong trend. So I promised you extremes. So the first extreme I'll show you is basically marine heat waves. And marine heat waves are basically when the SST goes above the 90th percentile of occurrence and lasts for at least 5 days. So here we have basically an average and an observation, and when it crosses the 90th percentile, it's category 1, moderate, and then we double it. And when it crosses double the anomaly, then it's a strong, then it's a severe 3 times, and on to extreme at 4 times the anomaly needed to achieve the status of a heat wave. So this is the story for the estuary in 2023. So this would be the mean, this dashed line, and the observation. And we hit in the fall, we reached marine heat wave status into even the extreme, and for about 2 weeks, and for a few months as a severe, and it tailed off as a moderate. And when we report this in State of the Ocean report, we show this kind of plot where the blue is the climatology plus or minus half a standard deviation. And this was the observations of weekly data, and gave us anomalies, monthly anomalies of 5 degrees C, which is really, really high. And temperatures, when we were in early October, the SST averaged over the entire estuary was still as warm or warmer than what we expect in the maximum of the season at the end of July. So this was really something. So marine heat waves, we also calculate heat waves based on monitoring sites. So we have high frequency monitoring sites at each of these little dots here. Most of them are thermographs installed on either the moorings or the buoys themselves, from navigation buoys from the Coast Guard. So this makes it easy for us. All we have to do is put a thermograph on all the buoys that we need monitored before they leave to be deployed by the buoy tenders. So we don't even need to go at sea. We just need to visit Coast Guard and install all these, and they get deployed automatically. And so heat waves can be described by many metrics. Here, some of days per year that we're under heat wave condition, the mean intensity, the maximum intensity, the intensity times the duration, and the count. And you can see from this table that the last 3 years in particular have been very strong in terms of heat waves in the Gulf St. Lawrence. Coincidence with the highest 3 years, of course, of AVHR RSST. But this is not from AVHR RSST. This is from these thermographs. So really good correspondence between, of course, our thermographs and the AVHR. Next, I want to go deeper into the water column. So I'll give you a crash course in the formation of the cold intermediate layer. And we start with this August profile with maximum surface temperature. And as we move into fall, we have this little blender here mixing the water column. And of course, the air is cold, so it's cooling the surface, but also we are creating a mixed layer here. And we progress to winter, and we, on average, mix about a mixed layer that's 75 meters thick, near freezing, to make sea ice. And although this plot goes down to 500 meters, very few areas of the Gulf St. Lawrence are actually that deep. Like all of the Madeline shallows here is shallower than 100 meters. So this 75 meters on average still corresponds to 45% of all the volume of the waters of the Gulf St. Lawrence. So we're cooling a massive amount of water to near freezing before we can make sea ice in the Gulf St. Lawrence. And then in spring, this gets recapped, restratified, rewarmed at the surface, trapping what we will call in the summer the cold intermediate layer. And it gets progressively warmer over the season. So now we're progressing to the month of August. So cooling faster at the surface, but still warming faster at the surface, but still warming at the cold intermediate layer. And earlier, when I showed the August to November, I was getting you focused on this cooling at the surface, but at the same time, the cold intermediate layer was still warming. And this will be the case until this layer basically catches up to it. And it becomes the fall mix layer, which will progress to the winter mix layer. So this is the family of basically the 4 seasons of temperature profiles in the Gulf St. Lawrence. And winter air temperature is a crucial driver for what happens in winter because we're forming this winter mix layer. It needs to reach near freezing or freezing before we can make sea ice. So it's contributing to both. And when we start making sea ice, then we get brine rejection from the sea ice. And that also contributes a little bit to the winter mix layer. And the mix layer then, what's left of it in spring becomes the summer cold intermediate layer. So you can see that there will be a link between even the winter air temperatures and what we can see in summer in terms of cold intermediate layer because it was born the previous winter. So the first thing we'll look at is ice, and as a data set here, we're using Environment Canada's Canadian Ice Service ice charts, weekly and daily, but mostly weekly for many of the products because the charts go back to 1969. And we'll associate it, if you're familiar with these, the egg code, there's a stage of development here from new ice to old ice. And we'll attribute their suggested thickness, mean thickness for each stage of development so that we can compute a mean thickness at every grid point and calculate an overall volume. So this chart that you can see on the web will transform into this equivalent thickness chart for our own use. So basically, this is what it looks like in the Gulf St. Lawrence. So this middle panel here is the 30-year climatology of ice thickness from less than 10 centimeters in gray to over 100 centimeters in deep red, and actually in magenta here. So 30-year climatology, the year where we had the most, and you can see a much younger Peter Galbraith here, standing on the ice from the early years of the helicopter survey. And we actually had to drill with all these extensions up to here to drill through this ice at this station. So it can get really thick, not by growth, but by rafting. So it gets to maybe 30 to 40 centimeters in thickness, but then grows a lot by rafting. And the minimum year was 2010, was mostly open water, except for a brief entry of ice from the Labrador Shelf through the Strait of Belle Isle. But this record of volume was actually broken this year in 2024, where we had some very thin ice formation in the Northwest Gulf, but none anywhere else. If we look at the metrics of sea ice since 1969, we have here in green duration from 20 days to about 100 days. Then we have our estimated volume in black, and area out to about 250,000 square kilometers, which is about the area of the Gulf St. Lawrence. And you can see that all these metrics are correlated with each other really highly. And they're negatively correlated with temperature shown in blue, where cold air temperature is high on this plot and warm air temperature is low. And basically, the area in duration are correlated at 80 and 83% of their variance is explained using air temperature. And we can use this relation with predictions of sort of climate change, trends of we'll lose 2 weeks of sea ice for each increase of 1 degree in winter air temperature, and this many cubic kilometers of sea ice in this amount of area. If we look basically at the trend of you can see this warming trend, right, with large interannual variability with the blue line. But if we just look at the last 15 years, this block of data since 2010. We've had 9 looking at area, or 10 looking at volume of the 15 lowest sea ice covers that have occurred in the last 15 years. So we look at 15 years, how many of the 15 have been part of the 15 lowest, and it's 9 or 10. So it's 2/3 of the last 15 years have been part of the lowest years. We can compress this again, this data set over time, because while I don't have sea ice metrics here, I do have air temperature. So we can use this as a proxy similar to what we did for SST. So this lowering trend for blue is actually a warming air temperature trend that I showed you before of 2.3 degree per 100 years. And if we look basically in the detail of this, the Gulf St. Lawrence has been nearly ice-free 6 times in its history: 58, 69, 2010, 11, 2021, and 2024. And these 6 times coincide with the only times that the air temperature has been 2.5 degrees higher than the climatology. So this is another climate change tool for the Gulf St. Lawrence. This line is trending down, so warming at 2.3 degrees per 100 years. And we need 2.5 degrees C to have no ice. So in another 100 years, we will have warmed enough that a typical winter will have no ice in the Gulf St. Lawrence. And occasionally we'll have a winter with a polar vortex, and we'll have sea ice again. So sea ice is connected to the winter mix layer, and how do we measure it? Well, I've been running this helicopter-based survey for 29 years now, where we sample the water column from a helicopter and stationary flight from about an altitude of 30 meters or so. And we do this every year in early March. So we're sampling basically this winter mix layer, its thickness and its temperature. And this is sort of the climatology of the temperature of the mix layer. And the special case of 2021, where there's almost no ice. And you can see that this panel shows temperature, water temperature, so near freezing only here. And this bluish kind of cold only coincides with the only place where there's any sea ice. And the rest of the Gulf was really, really warm, up to 1 degree C and more. So nearly 3 degrees above freezing at that point. So these are 3 more examples of 2003, the year of the maximum ice cover, 2010, our previous record where we had the warmest Gulf, and our new record of 2024. And this is the March mixed layer temperature. Near freezing just about everywhere. This is actually different to freezing point. So everything here in magenta is really close to within a fraction of a degree of freezing. And then in 2010 was the year we had the most heat content in the Gulf St. Lawrence, and some areas were over 2 degrees C above freezing. And in 2024, you can see that it's sort of bipolar. There's a little bit of the Gulf that has reached near freezing, but a lot of the Gulf hasn't. So if you look at sort of the making sea ice is a race between the air that's trying to suck the heat out of the ocean, and the ocean that's trying to keep it by the end of winter. Well, in most years, this race is easily won by the atmosphere, and we get sea ice in the Gulf by January, even December. And in a few cases, even by the end of winter in March, early March, the winter is finished, the air temperature is going to start to warm, but it hasn't managed to suck out all the heat out of the ocean, and we still have warm water, so no sea ice. A quick word on the predictability of sea ice, the sea ice cover based on current conditions. Since we do have all this coverage of the heat content from our fall survey and the winter conditions, we did look to see if we could predict whether we would have what kind of sea ice onset or severity based on the heat content of the fall survey, which used to be actually called the ice forecast cruise. So there's sort of a hint that this should be useful for this, but there's actually no relation between the upper layer heat content in the fall and either the date of ice onset or the severity of the ice cover over the winter. But if we look at the Northwest Gulf only, so it's kind of start to form in the estuary in the Northwest Gulf, we limit ourselves to that, and we track when the SST drops below a certain temperature, like -1, we know we're really close to making ice. So the relation between the date that happens and the onset of ice explains all the variance, or almost. And as we go back in time, we go to higher SST, then we increase the lag time, the lead time, and we introduce more and more variance. But still, at 1 degree C, when we cross 1 degree C and over this area, we explain 50% of the variance of the date of onset, and with a lead time of 30 days to 37 days. And if we take a step back and look at air temperature, which is actually forcing SST to drop, we get a result with less reliability at low air temperatures, but we still get something usable explaining half the variance when the air temperature crosses -2, and this gives us a lead time of 37 to 44 days. If we want to see what the seasonal maximum is going to be, which occurs in late February for area and early March for volume, and we go back in time, like in mid-February, we look at our current condition and how's that correlated with the maximum. And as we go back in time, this correlation drops, but we still get an R squared of 0.5 by mid-January for area or early February for volume. So this gives us a lead time of about 5 weeks. So if you really want to know, are we really going to have a strong ice year, a weak ice year? You can tell with fairly good confidence 5 weeks ahead of time, just by the conditions, with no meteorological forecast, but no more than that. So as I said, the cold intermediate layer is the cold water that remains from the previous winter. If we use a certain threshold temperature, say 1 degree C, that gives us a thickness that we can define and therefore a volume. And it's also characterized by a minimum temperature. So we can look at maps of those. So this is an old 30-year climatology, the previous one, 81 to 2010, of the thickness of water colder than 1 degree C by August. So we start off in winter, the whole Gulf is really cold, and it gets progressively warmer over time. But by August, there's still quite a thickness over between 75 and 100 meters of thickness that'll be colder than 1 degree C in that climatology. And this is the climatology of the temperature. And if we pick 3 locations, we see that spatially it varies quite a lot. It's much thicker and colder in the Northeast Gulf than in the Northwest Gulf. If we combine all these plots, we see that between a warm year in 2021 in red and a cold year in blue, there's about 2 degrees in variability in terms of the minimum temperature, but there's a 75-meter change in the deep thermocline depth. And that's related to both the temperature minimum and its thickness, and also the temperature at 200 meters, which has been trending warmer. So it's not to say it's all CIL, but it's a combination of cold intermediate layer and deep water temperature. And this has a large effect on the bottom area with thermal habitats suitable to snow crab in northern Gulf. Snow crab are interested in water temperatures colder than about 3 degrees C. So as this 3 degrees C threshold changes from 200 meters to 130 meters, then a whole lot of air bottom area suddenly isn't covered by cold water. And that's a really high impact for snow crab. So if we look at our warmest cold intermediate layer recorded, it occurred in 2021. So up here I have the new climatologies, 91 to 2000 to 220, of the thickness colder than 0 degrees C, thickness colder than 1, and minimum temperature. And the special case of 2021, where usually you go in August and you're still measuring temperatures colder than 0 degrees C just about everywhere, but there was hardly any to find in 2021. And even colder than 1 degree C was weaker than the climatology, the 30-year climatology for 0. And you can see by the temperature plots here that the temperatures are about 2 degrees C, well, warmer than the climatology. So if we look at the trending since 1995 volume of the cold intermediate layer, and the red here it's pictured colder than 1 degree C, and in blue colder than 0. You can see it trending down with lots of rebounds caused by strong winters with polar vortex intensity, really cold temperatures. So we get sort of a hammer effect on the winter mixed layer, and then we get suddenly a big CIL for the following summer. But you can see this trending down, and same for temperature, you can see it trending up. So you can kind of picture that the last 3 years, there's hardly been any water left in August that was colder than 0 degrees C. So this line's going to disappear, and at some point we'll have to make up a CIL definition colder than 2 to start plotting it above the 1, which will replace the 0. So the last 3 years have been really low. 2021 was a record low, 2022 was the second lowest, and 2023 was the fourth lowest. And it is related to winter air temperature and water temperature, but actually our best predictor for the cold intermediate layer is actually the volume of the winter mixed layer colder than 0 degrees C. So we measured this in March with the helicopter survey. We measured the thickness at every station. We get a volume of water that's colder than 0 degrees C, and we can relate that to the August temperature minimum. And the two are plotted on this figure here with the block line showing the March volume of the mixed layer and the blue dash line showing the summer CIL, and plotted one against the other in this panel. And you can see that we recovered 74% of the variance of the CIL just from the winter mixed layer volume. So it's our best predictor of CIL conditions. When I finish my survey in March, I can always go and tell people what the conditions are going to be. And the CIL is important because it sits on the bottom of the Madeline Shallows. So basically, the Madeline Shallows is at the right depth so that the bottom of the CIL it coincides. And the climatology for June here, these are a 30-year climatology for June and September. And you can see from the color palette that in June, most of the bottom area is occupied by temperatures between -1 and 0. And this warms, and by September, it's about 1 degree warmer. It's between 0 and 1. But there's lots of variability. In the coldest years, in August, we still have temperatures that look like the climatology of June, and it can get like 2 degrees warmer in the warmest year, 2021, where all of the area would be still cooler than 2 degrees C, good for snow crab, but a lot warmer. So what can affect that bottom temperature on the Madeline Shallows? It's a habitat that's consistently cold, but what can affect it are post-tropical storms. So this is another extreme event that I put in for you. So this is the track of Dorian in 2019, and it went over the Gulf St. Lawrence, going over some of our automatic buoys that we have deployed. And at this buoy IML-10, we have the top panel shows temperature. We had a temperature drop in a single day of 7 degrees C. We had salinity increase at the same time. We had waves reaching 12 meters. We had a wind gust of 110, 112 kilometers an hour. And we had the weather bomb with the atmospheric pressure dropping by 50 millibars in 24 hours. At the station East Southern Gulf, similar state and drop of 8 degrees C. And you can see that usually in blue, the climatology show that we get gradual cooling of the surface and we got instant cooling, which remained fairly stable. If I go back, see same thing at IML-10, it remained stable for like 2 months. So same sort of thing. We had waves here, 13 meters, wind gust 120 kilometers an hour. But this buoy is also equipped with a CTD profiler, measuring salinity and temperature down to the bottom. So every one of these little triangles is a cast. Unfortunately, we don't have a cast just before the storm, but we do have one like 10 days before. And the temperature, we see the same temperature drop of 8 degrees C at the surface, but at depth, at 35 meters, we see an increase of 7 degrees C. And if we take the average over 45 meters, we get the same average temperature between the before the storm and after the storm. So if you look at SST from AVHRR, just the week before the storm, the week after the storm, huge cooling. But this heat didn't go to the atmosphere. It was mixed down into the water column. And this stable at 35 meters habitat of 1 degree C just shot up to past 8 degrees C. So imagine you're a snow crab, you're happy all year round at this very cold temperature, and suddenly you get exposed to really warm temperature. So same thing for Fiona, which was followed just about the same track just a few years later. And again, similar temperature drop. And at IML-10, we reach waves of 16 meters. And that year we have a mooring deployed at our monitoring station in Hanesiak Valley. So this is a 1-year mooring of temperature with sensors at various depths. And we could see that this little box here indicates the passage of the storm. And basically, the temperature went at 50 meters from 1.6 degrees C to 8.4 degrees C. So it's really, really high injection of heat down to the bottom to the seafloor. And even at 60 meters, it went up to 4.7 degrees C. Lastly, the quick note on what's happening in the deep waters of the Gulf St. Lawrence. These waters are a mix of cold Labrador current waters coming down around the Grand Banks and of warm Gulf Stream waters, and they get mixed together around here. They take about 2 years to reach the entrance of the Laurentian Channel, 2 years to get sucked in by estuarine circulation to Cabot Strait, and 3 years to reach the St. Lawrence Estuary, and a couple of years to reach the channels in the Northeast Gulf. And one way to look at them is just to look at the deep temperature maximum, which we can map. And I show here maps of the deep temperature maximum over the Gulf St. Lawrence starting in 2008, because 2009 was like the last cold year that we had. In 2010, we saw waters above 6 degrees C appear. And we move up and we saw 7 degrees C appear for the first time in 2012. And you can see these waters progressing to the heads of channels a few years later. And this black line shows 7 degrees C contour, and the white line shows an 8 degree contour that started to appear. And this reached in 2020, the 7 degrees C reached the Northeast Gulf and basically invaded every crevice in 2021. And in 2022 was the warmest condition of the Gulf St. Lawrence. And we had a slight cooling in 2023. And if we compare 2009 to 2009 with 22, then we see that on average, we went from 5.2 degrees C to 7 degrees C. So a really large difference compared to anything that happens at the surface. Long term, we have data since 1915. These are lines for 300 meters, 200 meters, and 150. And every year after 2015, 2016 was a 100-year record. And 2022, all these depths were at 100-year records. And we had reached sort of like the peak Gulf Stream content. There's no Labrador current water content left. So it was sort of as warm as it can get. And if we look at basically the temperature at Salenti, the typical Salenti found at 300 meters, it tracks really well the temperature found at 300 meters, showing that this is basically a change in water mass type from really 100% Gulf Stream. However, the high variability at shallower conditions are shown here by the black line. That's the temperature at a salinity of 34. And you can see that we saw some much higher interannual variability that wasn't caused by water mass changes, but it was actually caused by the halocline heaving up the water column. So in 2022, the halocline was 16 meters higher in the water column. So explaining the peak that we got that year. So these are box averages along the Laurentian Channel from the mouth out to the estuary. And we could see basically anomalies trending over 5 years between the mouth and the estuary. And we kind of were catching a break here. For the first time, we see temperatures below 7 degrees C average over the mouth of that area. So we expect some influx of Labrador current water to cool the Gulf just ever so slightly. But we have a long ways to go before we reach a record of 2015. So in summary, the summer surface temperatures, they track the increase in air temperature, 1.1 degree per 100 years. The last 3 years were the warmest on record for the May and November conditions. We had high occurrences of marine heat waves. For sea ice, there's 6 years with almost no sea ice at all, and they coincide with a temperature anomaly of 2.5 degrees C in winter. These winter air temperatures are increasing twice as fast as in the summer, so we can forecast that at some point there just won't be any sea ice in those. The cold intermediate layer is what remains of the winter mixed layer, and it's correlated with the winter mixed layer volume. It's been warming and thinning since '85. But it still affects the thermal habitat of snow crab on Madden shallows, but it's affected by post-tropical storms, which can bring in heat that will last for several weeks, even months. In deep waters, we have record temperatures set in 2022, 100-year records, basically, and we've been sort of stabilizing since, and we hope that it might be cooling. That's all I have.
Thanks very much, Peter. Merci beaucoup. That was a very interesting presentation, and I'm particularly impressed by your graphs and graphics and the extent to which you've been able to analyze the data. We are getting some questions coming in, so maybe I'll start by reading the first one from Eric Oliver. He says, if the CIL temperature-based definition is arbitrary, as you said, we will need to use a 2 degree C definition soon. Then is there an objective definition we can use that is based more on the physics, i.e. the layer that is sequestered from the surface in spring and summer?
Well, that's a good question. Well, actually, it's kind of what we're doing by using different thresholds. In the Maritimes, they have to use, on the Scotian Shelf, they have to use 4 degrees C. And on the Newfoundland Labrador Shelf, we use 0 because the waters tend to be much colder. So yes, as the climate changes, it gets warmer, we'll be looking at what layer just gets formed, and whatever temperature that is, we'll have that definition. That's a good point.
He then further observes this could then be more applicable in other locations where the same physics of CIL formation apply. So
Yes.
that's kind of what you've addressed there. Thank you. A question from Ruping Mo. Could you give some comments on the predictability of marine heat wave events? Are marine heat waves forecast routinely?
That's a good question. I don't tend to do forecasting. I'm not an operational, I'm not in ocean or operational oceanography, that sort of modeling side. So we just do tracking of one issue with the mere definition of marine heat waves, of course, is whether you detrend or don't detrend the series. Because of course, as the temperatures are getting warmer, then it's based on the 90th percentile of the 30-year climatology, which we're creeping out of. So there's more and more and more heat waves because we're creeping out of the, so I'm sort of two minds even about that issue, because, you know, if we keep resetting the climatology as we do every 10 years when we shift all these climatologies, then we're sort of wiping away climate change at the same time. Whereas we might want to remind people that the climate is actually warming. So I'm not answering this question at all, I realize. Sorry. No, we don't really do any forecasting. I'll leave that to the operational side of meteorology and oceanography.
Thanks, Peter. So as a question from Serge, what is the impact of the disappearance of the winter ice in Gulf on the overall Gulf of St. Lawrence temperature? I'm thinking like the analogy of the isolation of the snow over land. If the Gulf surface loses this isolation layer in the winter, does it have a big impact in the long term?
Well, you'd think so. I mean, right. Ice acts as an insulator, right? So when you start forming sea ice, apart from the brine rejection, you're sort of capping your mixed layer, and you're no longer forming, thickening your winter mixed layer. However, if you're making sea ice, you've already reached at least a freezing point. So you're insulating a cold layer up until the ice melts, keeping this layer colder. Whereas when there's no ice, the water is usually even above freezing to begin with. And as you get spring warm outbreaks, air outbreaks, you can start to warm the mixed layer while it's still well mixed, and the heat is easy to get from 50 meters deep out of the water column because it's well mixed. So there's that sort of impact of, as you get no sea ice, then yes, you're getting an easier to extract heat content from the winter mixed layer. And you have to wait until it stratifies by heat, because you've got no sea ice to freshen it, before you can start to hinder that mixing from the stratification to insulate the cold intermediate layer. So that's a new effect, which we haven't really looked at very much, or at least I haven't, in terms of even my relation between the winter conditions and the summer cold intermediate layer, I know are different, because I even sometimes measure conditions in early March that have warmed since the sea ice peak. In weak ice years, the ice peaks earlier in February, and I might even be measuring something, a mixed layer that's a little bit warmer than it was at the peak of sea ice, just because there's no protection, it's all one mixed layer, it's easy to suck heat out of it. It's a very good point.
Thanks, Peter. Next question from Sam Anderson. He notes this is a pretty incredible overview of climate change expression in the Gulf of St. Lawrence. Thank you.
Thank you.
My question is, what comes next? What are your future research priorities, and how can the information you presented today be used to inform better policy?
Well, I'm 5 years away from retiring. So what's next is trying to finish up a whole lot of some of the stuff is still in my head and not written in papers. So there's that. In terms of affecting policy, all this is really done basically to affect policy in terms of at least fish quotas and so forth. That's why we exist at DFO. So I give state of the ocean advice. Every January, I give this sort of presentation for the conditions of the previous year, and all stock assessment biologists attend, and other factions, sectors within DFO also listen in. And so, yes, of course, we want to feed in through to stock assessment using the ecosystem approach that's being implemented by DFO, because certainly all these things have impacts on various species. So it's a team effort with all the biologists, but of course, we also hope that it makes its way to other government officials and other departments that notice, oh, okay, Gulf St. Lawrence is warm. So, but I do a lot of media interviews. In the last 10 years, I've done about nearly 300 media interviews. So it's sort of hitting that nail every time that I can, using that sort of public access.
Thanks, Peter. And there's one, I think this will be the last question that we have time for, from Nancy Suntian. Thanks for the very interesting presentation. Are there advective sources of the CIL? Oops, it bounced into the Gulf of St. Lawrence.
A little bit. The March survey also serves to monitor the inflow through of Labrador shelf water through the Gulf St. Lawrence. But on average, it's only like a 15 to 18% contribution to the overall volume. We also have a long-term ADCP mooring there, and we have a paper published last year where we compare the 15-year or 10 to 15-year time series of ADCP with the volumes that I calculate of Labrador shelf inflow into the Gulf St. Lawrence. So basically, this is done by temperature salinity criteria. The water that's inflowing in winter into the Gulf St. Lawrence is too salty at that temperature to have been formed locally. So it has a completely different TS signature. If you look at the TS signature of the Gulf St. Lawrence, it sort of looks like a V, where with the bottom of the V is the CIL, and then it goes up again with higher salinity of waters from the deep layer. And in the winter, there's a little near freezing hockey stick that sticks out of that V to high salinities in these waters that have inflow through the Strait of Belle Isle. But it's a minor contribution, but we do account for it. In terms of through Cabot Strait, there's possibly some warm water coming in. There's always a patch of warm water on the Port-au-Basque side of the Gulf, on the southern Newfoundland, southwest Newfoundland. So that's always where the water's warmest. But it's like two things. It's like also where the waters are cooled last, but it's also fighting against possible advection coming in through the strait on that side of warmer water. So bit of both.
That's great. Thank you very much, Peter, for a most interesting and stimulating presentation.
It's my pleasure.
Yeah, thank you. Just before we close the session, just a reminder that in about 15 minutes, we'll be opening up the poster session. So where you can view the posters and meet online with poster presenters. Following that, we'll have another 90-minute oral block, or a 90-minute oral block. And then the end of the day today is the awards ceremony. The awards ceremony is public, and there's a separate Zoom link for that. So it's outside of the Event Mobi platform. I sent the Zoom link in an announcement yesterday. So you can click on that Zoom link to attend the awards ceremony later on today. Thanks very much, everyone, and thank you very much, Peter.
Thank you.